Okay, so in this shortest session, I'll go through these different kinds of resonators. As I mentioned, we have discussed many of these in the past as well, in various forms, and also in microwave office, we have seen it. But I thought I'll just go through it slightly more formally based on the discussion poser. I wanted to point out a few things which are slightly different here. So parallel LCR circuit, everybody knows here. So here you have an L and a C and an R as well. Okay. So at the very outset, I want to ask you, from the perspective of microwaves and all the things I've been saying, is there something odd about this circuit? I've already said there is something odd, but what is the way it's drawn here? Does not have an very good, right? This, of course, is showing an ideal voltage source. In that respect, it's fine. But what we have learned in so many times is that in microwave, it is not possible to make a voltage source like this. Okay. For analyzing the properties of the resonator, it's still fine. But having a source impedance here versus having a resistance here actually changes something about what that resistance does to the properties of the resonator. Okay. The simplest thing, of course, is that if I do put a resistor here, and let's say this is called, let me call it Z0, then if I want to think about the dissipation for this LC oscillator, which is this part is the reactive part, right? And these are all the dissipative parts. What will be the total dissipation for this circuit if I did put a source impedance Z0 as well? Will it be? They will be in parallel. You were saying Z0 plus a series, no, right? So this is, remember, we have already done this. So the impedance of the voltage source is basically 0. So this Z0 is actually the same as being connected across these two. So it will be 1 over Z0 plus 1 over R whole inverse is the total thing. So, but that for a parallel LC circuit, is it more dissipation or less dissipation compared to the case without the Z0? No, so Z0 in parallel with R, is it greater than R, less than R, or equal to R? Less than R, right? And if it is less than R, in terms of this LC circuit having more dissipation or less dissipation, if you have smaller R, is it more dissipation or less dissipation? Exactly. We discussed this, right? The quality factor for a parallel circuit is RC omega naught. Okay. So the smaller the R, the smaller the Q factor, which means more dissipation. The way you can think about it is that the power dissipated goes as V square over R. Right. So the oscillator is going to set up some voltage depending on the level of excitation across it. And the amount of power dissipated is going to be that voltage, which is the voltage at this point, over R. Okay. So this was one of the things. Otherwise, here, the analysis they are doing here is basically to define Z in. That Z in is basically the impedance between these 2 points. And that just is the parallel combination of 1 over R, the J, the L, and the C reactance is the whole inverse. And that has a resonance So remember that they have actually plotted the impedance here as a function of frequency. And that has a maximum value. Now, because R is present here, this value reaches a maximum of R. Because otherwise, remember, a parallel LC circuit has infinite impedance on resonance, right? So infinite in parallel with a finite value R means it's the value you will get is R. Okay. And then at other frequencies, it will go down. This will not happen if this resistor did not exist, in which case you only, and even if this resistor existed, Z in will still blow up, right? But Z in is not really what you can calculate it, but from a point of view of reflection coefficient, you then have this as your source, and then the rest of this part is basically a dissipation free circuit. So we had talked about the fact that in steady state, all the power will be reflected, and then you only see the information in phase, right? So the difference between the dissipation coming from a source impedance and some other resistance, which is part of the LC circuit. So this R could be modeling some material losses in the L or the C circuit, right? That's one way of modeling it. That basically is what we often call as Q external and Q internal. Internal meaning part of the resonator itself. So in this case, because it's all in the two come in parallel, Q internal is actually RC omega naught. Q external is Z naught C omega naught. Okay. And total Q, which is related to the total dissipation, is 1 over Q total is 1 over Q external plus 1 over Q internal. This is just because the R's add inversely because they're in parallel. The Q also adds like that, because the Q's are just proportional to the R's. So this terminology you might often hear about internal Q versus external Q. From the point of view of microwave measurements, when you in general have both, then if you do have an R here, which means Q internal is finite and it's not infinity. Again, you have to remember that R equal to 0 is not the no dissipation limit. R going to infinity is the no dissipation limit. So similarly, Q internal going to infinity means no internal dissipation. That is the limit where you have no absorption by the device. But you can also have a situation where Z naught and R are the same. And in that case, your Q external and Q internal are the same, and you get something called critical coupling. And in that case, what's going to happen? The Z in at this point at resonance is going to be R, which is equal to Z naught. So it looks like a matched load at that frequency. So if I plot gamma, then I will get a zip which basically goes to 0 exactly on resonance. Why? Because on resonance, R is the same as Z naught. For all other values, it will be less than, greater than 0. Okay. If Q external dominates the total Q, which means that Q external is much less than Q internal. Okay, so this you have to keep getting used to this reverse argument. So I said Q external dominates. You would think Q external is bigger, right? No. Dominates means that it contributes most to Q total. That Q internal doesn't play a role. And because of the inverse relationship, if Q external is much less than Q internal, this is called overcoupled. Okay. If Q external is much less, sorry, other way around. What's going on? This is called undercoupled. And if Q external is equal to Q internal, then it's called critically coupled. Okay. So critical couple was the case where you have the gamma going to 0. In both undercoupled and overcoupled, gamma will not go to 0. But there is some kind of crossover which happens. So if you start from no internal dissipation, you are overcoupled. You keep increasing the internal dissipation, you come to critical coupling, gamma comes to 0. And then you increase the dissipation more, then you become undercoupled. Gamma doesn't go to 0 again. But from looking at only the gamma plots, you cannot say whether it is undercoupled or overcoupled, because in both cases it is above 0. So you have to look at the phase as well, or you can look at the real and imaginary parts. And I think we had discussed this in an earlier lecture where I had shown you the responses. So we can also take a look at that in just a second. So what that means is that which resistor is dominating the dissipation, whether it's the internal losses or the losses which is coming from the fact that you have an external source coupled to the device. This is sometimes also called as the coupled Q. The Q total is also called the, sorry, not the coupled, the loaded Q. Okay. And this is sort of it comes from people, these definitions come from different angles. I'm so used to thinking that everything has to be overcoupled because that is the way we do our experiments. We don't want our oscillators to have any dissipation inside. Our entire dissipation comes from the fact that we are connecting an external environment to that oscillator in order to probe it. And we want that to be the only dissipation if we can, get to that limit. So the load here means that the fact that the external device is connected to it. And that loading adds an additional dissipation as opposed to whatever the internal dissipation is. So sometimes this is also called the loaded Q. Okay. What else? Yeah. So basically, that's sort of what is for the parallel. Here they analyze they define exactly what the Q factor definition comes from. This full width, half bandwidth argument, and then how this formula comes about here. Okay. The same analysis is done for a series LC circuit, which actually starts with that. I wanted to do the parallel first because that's what we are familiar with and typically use more in our kind of experiments. Now you have LCR. Again, there is no Z0 here. And here it will play a slightly different role. Now the two things will add if you put a Z0 here. But you can have this series LCR circuit. The resonant frequency is, of course, the same. Z in, seeing from this point, now goes to R at resonance. Even that one went to R. This also goes to R, but from the opposite direction, right? So it starts with high impedance. And then because the ideal LC circuit has 0 impedance on resonance. But if you have a series R with it, it will go to R. Okay. And then the Q factor here is 1 over omega RC. It's basically the inverse of the case of the parallel case. So here, small resistor is good, because now the relevant term is the current flowing through the LC circuit is the same as the current flowing through the resistor. So the power dissipated is I square R. So the smaller the R, the less the dissipation. Okay. So So this is basically 1 over that expression for the parallel case. And everything else, sort of the arguments remain the same. I can now define a plane here and put a source resistance here and define a reflection coefficient. So that will just be Z in minus Z naught over Z in plus Z naught. Okay, so let me stop this and move on to the microwave office. Okay, so this is now the simplest case. No internal dissipation, but this 50 ohm port is going to give you dissipation. Oh, I did start the recording. Good. Not sure. Is it recording or is it not recording? We plot S11 first. Magnitude. Let's look at the angle. Okay, so you remember this plus 180 to minus 180 kind of behavior goes through resonance at 0. It's useful to look at the real part of this guy. So it has this nice kind of peak type of behavior, peaks at resonance, and full width half max here gives you the bandwidth defining the Q. So Q divided by full width, omega naught divided by full width half max is the same definition as the Q we have done. That should give you RC omega plasma. Okay. Just for reminding you, the imaginary part looks like that. And the magnitude has no response. Okay, it's flat as expected. Some things to sort of, these are things to remember, that in the case of overcoupled, or see, this is completely overcoupled, right? There's no internal loss here at all. The full width half max point is also the point where the real part crosses the 0. Okay, because the full width half max, the maximum here is -1 to +1, it's 2. Halfway point is going to be at 0. So these 0 crossings are the same point. If you look at the same points in the imaginary part, these are these points here. where they reach the maximum value and turn around. Okay. So these are convenient points to know if you're if you're looking at a reflection coefficient of an overcoupled oscillator, then you can look at these points and compute the Q. You don't even have to compute the full height. I'll tell you what happens when you have some amount of losses. This is also the point where the angle goes from plus 90 to minus 90 degrees. Okay, so let me just show you this for here. I'll add a marker and I will adjust the frequency so that this is close to plus 90 degrees. And let me add another one here. Adjust this to minus 90. Let me also add the 0 point. Okay. It's close enough to 0. So if I now shift to the real part, you will see that the peak, the 0 phase is now at the peak, and the plus 90 and minus IT are exactly where the real part is 0, right? So the real part is 0 at those same frequencies. The marker positions have not changed. And I go to the imaginary part now. So the resonance is now where the imaginary part goes through 0. And the plus minus 90 points, or basically the bandwidth defining points, are the point where the imaginary part goes close to 1, right? Or exactly 1 in this case. In a real measurement setup, things are not normalized as nicely here, because here the reflection coefficient is measuring exactly the device. In a real experiment, there'll be lots of cables and there'll be gain and other things. So these things will not exactly go from 0 to 1 and minus 1 and back, but they will go from 0 to some maximum value and come back to some other maximum value. So you have to reinterpret these points as the maximas and not as plus 1 and minus 1. Same goes for the real part as well. Okay. So let me go back to the real part and I'll now start adding some dissipation to the problem. So I now add a resistor. In parallel. And I want to start with small dissipation, which means large resistance. Okay. So I'll set this at 1000 to begin with. Let me put a tuner on that. Okay. So the first thing you immediately notice looks mostly the same, but you see that this peak now has fallen down. Okay. It's no longer at 1, it's at 0.9. The moment this happens, the Q definition cannot be taken from these 2 points, because now the full height has reduced. So you have to find the distance from this flat region to this one. So it's 1.9. Half of that is going to be 0.95, which means you have to choose the point where this is minus 0.05. That is now the new bandwidth. These 2 points actually remain the same. So in one way, you can say that this bandwidth, as measured by the zero crossings, the 2 zero crossings, is a measure of the external Q. Right? Because external Q is still the same. The external Q is set by the fact that there is 50 ohms. Let's look at the tuner here. And let me make this value larger. You see that that doesn't change so much. So as I keep lowering this value, the peak starts to drop. Now I'm at 500. Let me Okay. So yeah, so that again, I think that only works if the dissipation is not very high. So that's not really a good point. So just ignore that. The zero crossings don't really have any specific meaning once the dissipation becomes very high. It's not at the same point. But you see the peak starts to drop. If I now come to the situation where it is critically coupled, the real part comes up to 0. So this is actually how from the reflection coefficient, you can know whether you are overcoupled, critically coupled, or undercoupled. Because below this, the real part goes below 0. So again, in a real experiment, this extreme limits on the right side will not go to -1. It will be some minus x. But it will come up to 0 and go to plus x if it was lossless. If it was critically coupled, it will come up to exactly 0. It is undercoupled, it will be below 0. Anything above 0 is overcoupled. Okay. So that's actually how you figure out. And from the ratio actually of this peak height here, like what is the value here, actually allows you to calculate the value of the internal Q and the external Qs. By fitting this graph, you can get all the information you want. The same thing if you now look at it in the imaginary part. So remember, right now we are undercoupled, right? And the resonance is still the same point, but these peaks have come down significantly. Right? So if I set this to critical coupling, this peak here goes to 0.5 as opposed to 1 before. Okay. So that's the equivalent way in imaginary part. You can find out that if the maximum peak here is 0.5, but that's very tricky because 0.5 of what? Because 0.5 here is with respect to 1, and you don't have access to the full value. So you have to look at the real part and say that, okay, the extreme values are at minus x. Then you can say that, okay, is this x point x by 2? Okay, so that reference scaling has to be looked at. And when the same thing happens in phase, you see the change of the direction of the phase shift. And so let me go back to being somewhat overcoupled. And I will shift to phase. So you see, this curve looks like what we had seen before in the completely overcoupled case. But as I bring this closer and closer to being critically coupled, so I keep changing the wrong thing. So I'm at 150 ohms. This is 100 ohms. This is 60 ohms. So what you actually see something very strange, and this can be very misleading. You generally associate high Q with a sharper resonance, right? High Q means less dissipation, resonance is sharper. But when you look at the phase, it actually does something opposite. So this is, where I've minimized the external dissipation is only 200 ohms compared to the 50 ohms. So 50 ohms is still dominating. And this is how the curve looks like. Let me freeze this. Now I set this to 100 ohms. Oh, I'm changing the wrong one. So you see how the line looks sharper? I go to 60 ohms and it looks even sharper. And exactly at 50 ohms, it's actually discontinuous. So you see what happened here? And then immediately jumps like this. Okay. And then if you go undercoupled, then you actually, the phase goes up like this, and this very sharp jump is just the wrapping of the phase around 180 degrees. Okay. So the actual phase shift is going something like this, like from here. I can sort of continue it like this and make it like this. It's like taking this part and putting it on top there. So in a network analyzer, if you're not set correctly and you hit auto scale, you will actually see a much smaller phase shift, and that tells you that it's undercoupled. So by looking at this real, imaginary, and phase shift, you can tell what's going on, and by fitting to them, you can compute all of these parameters, that what is the internal loss and what is the external loss, and things like that. So you have to be careful about this, and this plus minus 90 argument and the 0 for the real part and the plus minus 1 argument only works when you are in the deep in the overcoupled regime. Otherwise, the more robust quantity is the full width half max of the real part. And that always gives you the correct definition for the line width of your resonator. Okay. So if I now look at this LCR circuit, and instead of looking at the reflection coefficient, let me make a new graph. And I plot Z in, just like they did in Ozar. And let me plot the, I guess I should plot real and imaginary part. Okay. So remember, right now, we are having a value of 200 ohms for the internal dissipation. And you see that the Z in at resonance, real part goes to 200 ohms, imaginary part goes to 0, right? So this is what we had seen. If there was no internal dissipation, which means R going to infinity, this will basically do the same thing. So the magnitude blows up to infinity. So the next part to discuss is that, do sections of transmission lines also give you the same kind of behavior? And this is basically about now constructing transmission line based resonators. And our definition for resonator is something which has either a series LC type of response or a parallel LC type of response. Okay. So I'm going to make a new schematic here. And I will put going to make make it now all sources so that I can look at both the schematics input impedance, real and imaginary part. Of course, there's a problem because the one of them is going to I'll just fix the scale. Let's look at this carefully. I've made a section of transmission line, which is 90 degrees in length at around 5 gigahertz, no, at 5 gigahertz, has a characteristic impedance of 50 ohms, and it is shorted at one end. Okay. Why did I make it a short circuit? Because I was trying to look for something whose impedance is very high at resonant frequency. And I know that the lambda by 4, this is a lambda by 4 transformer. It will take a short circuit and turn it into an open circuit, right? Let's look at the colors here carefully. The brown one, which is this one here, is the original LC parallel LC circuit, and its real part goes to a maximum of 200 ohms because there it had some dissipation in it, right? Then the blue one is the imaginary part for the parallel LC circuit. The the red one hourglass figures, which is here, is the real part of the transmission line based system. And that's just zero because it has no real part. You can barely see, but it's a zero, just going flat here. And the green one is the imaginary part of the lambda by 4 shorted section. And if you at least compare the blue with the green, it looks like it sort of has the same shape, right? And it's blowing up to infinity. Let me just kill the real parts and you can only look at the imaginary part. Right? So it's sort of similar, but it's not really the same. But of course, there is also the problem that the parallel LCR I have right now has dissipation. This one has no dissipation. It's a lossless one. Let me just see what happens if I increase the value of this to some large number. Does it start to match better? What are we trying to do? We're trying to see if there's a circuit which will have the same kind of response as a parallel LC circuit, right? And then we can say that that's going to have the same kind of behavior. So this is currently at 200. Let's see what happens if I set it to 20,000. Okay, so this value is going up to basically go to the same, some very high number, but the shape is not changing. Like this is far away from here. Okay. What should I change for these two to start looking similar? I just changed the resistance. Z0. Exactly. Because the resonator we have made had a particular choice of L and C. And the equivalent thing you get from a transmission line resonator depends on the Z0 because that's what tells you how much L per unit length and how much C per unit length is coming. And that equivalence is what gives you the effective circuit, which is the equivalent LC circuit. So if I now make the Z0, where did Z0 go? That's this one. If I make it larger, it's going in the wrong direction. So that means I have to make it smaller. This is a 25. Okay, somewhere around there, it starts to match. Okay. So anyway, this was the point I wanted to make, that it's the characteristic impedance of the transmission line which determines the effective LC circuit. Because remember, otherwise the other number is frequency. So frequency is fixed and that is set by the length of the transmission line. how much inductor and capacitor, because any combinations of L and C will give you. But it's basically the same argument that this ratio of L to C can be thought of as the characteristic impedance of this LC circuit. The transmission line will be related to it. It will not exactly be the same. So Posar has a section. So I want to stop in another 5 minutes, but I'll quickly show you that section. But that's basically how you decide. So depending on the LC circuit you want to mimic, you can do that with, if it's a parallel LC circuit, you can do it with a lambda by 4 section, 90-degree section, which is shorted at one end. You can also do it by a lambda by 2 section, which is open at one end. So let's take a look at that. That will have a slightly different dependence for the LCs. But it's the same idea that a 180-degree section inverts, doesn't do anything, right? It's not 1 over. Lambda by 4 inverts the impedance. A 180-degree impedance just takes open to open. Oh, sorry, I should not have anything here. It should be an open circuit here. Now let's compare the response now. Okay. So now you see that this one is no longer matching because now I need a different characteristic impedance, slightly higher to match. Okay. Why is this? It's because the length is longer. The capacitance per unit length, if it is the same, the total inductance and capacitance is related to both the length and the per unit length values. Because we wanted the same L's and C's as the previous case, now I have made the length longer, so I have to make the characteristic impedance a little bit higher to make the same matching. But now you already, one thing you start to see that this matching is not so great anymore, right? It looked kind of nicer for the previous one, and you now start seeing other things happening. This, of course, is the fact that transmission lines have periodic properties. So these models are only approximate in the sense that right near the resonant frequency, they are very accurate. But as you go away from the resonant frequency, they are no longer accurate. And that basically boils down to the fact that are you making a very high Q oscillator, which has a very narrow line width, so all the action is happening at small frequencies, then the transmission line model is fairly accurate for that model. Otherwise, you will not be able to get. So this is sort of, again, a rule of thumb. It's very difficult to make low Q oscillators using transmission line resonators. For that, lumped resonators is better to do. But for high Q oscillators, you can do that. Okay. So for a parallel LC, you can either use 90 degrees at with a short on one end, or 180 degrees with an open at one end. And for a series LC circuit, you can use an open with a short circuit, sorry, a lambda by 2, 180 degrees with a short circuit. Because of the same argument, a series resonator will have 0 impedance on resonance. So if I have a lambda by 2 and I keep it shorted on one end, it will also look like a short at the other end. And you can verify this by looking at the series LCR Zin. Okay. This is a really annoying problem. How does it? Just cannot figure out how to come out. Damn thing. Sorry? But I don't want to quit any disk. I guess I could quit any disk as well. Okay. What I want to do is stop share. And quickly share screen here. Okay. So here they talk about the shorted lambda by 2 line. That is the case for the series LC oscillator. And here, I mean, this is the case we haven't looked at, but here's where you get those equivalent values, right? So the inductor of the equivalent LC circuit for a given transmission line, in this case, shorted lambda by 2, is given by Z0 pi over 2 omega naught. And then C, you can just compute from 1 over omega square L, because that has to match the resonant frequency. Similarly, if you now go to a short circuited lambda by 4, which is the first thing looked at, that's for a parallel LC circuit, you will similarly get a different formula for the capacitance. Okay. And they also give you the formula for an equivalent resistance that will only come if your transmission line is lossy. So remember, this factor alpha is coming in. The alpha is usually the attenuation factor inside a transmission line. We have only used lossless transmission line so far. So this will then give rise to a Q internal, right? The Q external will come from the coupling of the transmission line to the outside world. And so far, what we only looked at was a transmission line with some boundary condition, and then there's a 50 ohm port here. But you can also put things here. So instead of 50 ohm connected directly, you can actually put a capacitor. And that basically reduces the coupling of this circuit to the 50 ohm and gives you a higher external Q. Right? So most practical high Q resonators are made by putting a very small capacitor here. The transmission line picture of thinking about this, or thinking about it like optics, is that you have two boundary conditions or two mirrors. This short circuit is like a perfect mirror, but this weak small capacitor is like a partially transmitting mirror. So light will bounce back and forth, but it will also leak slightly from here. This is how Fabry-Perot resonate as a mirror. You have one perfectly reflecting mirror and one partially transmitting mirror. So that's what these resonators are like. The fact that you can always model them as an equivalent LC circuit near resonance is true for even optical resonators. It's just a model. And then you can calculate the equivalent C's and L's using this kind of a stuff. But otherwise, these sections of transmission lines are basically waveguides with boundary conditions which set up the standing waves in the setup. So these are alternate ways of thinking about the same thing. Okay. So you can go through this section. It's fairly straightforward. It sort of tells you how these numbers are arrived at. And you can see that the capacitance value is inversely proportional to Z0, which makes sense because more capacitance per unit length means smaller Z0, which means larger C here. And then vice versa for the L case, right? So those kind of things will come, but there are these factors of pi and 4, which come in because of whether the length is lambda by 2 or lambda by 4. So those things come in. It's sort of some kind of an averaged capacitance over the entire length. It's not the same as capacitance per unit length into the length of the transmission line. That is not the formula because the field is not uniformly distributed over the entire section. So you have like an integral to compute that. Okay, so let me stop there and we will finish this up and move on tomorrow at 11 o'clock. I'll check, maybe we'll do it here. Hopefully nobody has any classes happening at that time. I'll probably combine it into one long assignment and send it off tomorrow. So you can basically finish it and submit it at the end. Yeah, all of the recordings I'm going to upload and I will share.